Thank you very much, everybody, for joining us for this workshop about the Spectra package. Yeah. Again, if you're interested, stickers, feel free to drop me an email, and I'm happy to dispatch them as widely as necessary. So I don't think Johannes needs any introduction. He's really well known among the community, the bioconductor community. He's one of the main developers of lots of important packages, in particular Zenbase, MZR, XCMS, and now also the new set of packages that are part of the R4 Spectrometry initiative. And he's going to talk about Spectra and how you can use Spectra to compare to cluster Spectra. So Johannes, if you need anything, let me know. But otherwise, I think I'll just mention in case there are questions.
Okay, excellent.
I won't interrupt you.
Thanks, Laurent, for the introduction. I just would like to briefly go to the workshop here. So basically, we are in the seamless integration of mass spectrometry data workshop, and so that's. I mean, it's a pretty long title. The goal of this workshop is actually that I would like to give you sort of a live demo of the functionality of the Spectra package that we recently added to Bioconductor, how it can be used to analyze mass spectrometry data using a very simple, let's say, use case in which we want to match or compare experimental MS spectra against a public spectral database. And so for participating, what you can do, so there's this amazing cloud available. So if you go to this slide here, I think maybe if Laurent or Christophe can post the link also on the feed. So there is the cloud available, and on page 5 there is also this workshop. So you could, for example, now I would suggest you launch it now, because it takes some time until this all the Docker image is downloaded on the cloud. And for other people that actually have Docker installed locally, a way to run this is also simply pull the Docker image for this tutorial, and then start the Docker with this command here. That's what I'm going to do now. My local computer. And so basically what you can then do is go with your browser to this address, to localhost 8787, and you can log into the RStudio version, RStudio server version that's running inside the Docker image. So before we go, however, into this, let's say, workshop, into this live demo, I would like to give you a very basic introduction also to the topic here. Actually, maybe might be a good time to ask for one of these yes/no questions to the audience. So, how many people or who has already worked with mass spectrometry data? Can somebody maybe hold that?
Yeah, Laurent, I can take care of that if you want. So people are responding.
I cannot see any results anywhere. So you will have to tell me.
So for the moment, 69% said yes, 31 said no.
Okay, so we still have some people that don't know mass spec. That's great. So it means that it makes sense that I give you a very basic introduction also to that. So what I will explain here is a simple setup, so LCMS setup, how we are using this also, for example, in metabolomics or untargeted metabolomics. So just very in simple words, what we are doing here, so we have a sample that has our metabolites, our small compounds in it. So the advantage here is that we don't have to break down to peptides. We can simply measure them. So this sample is then, after sample preparation, injected into the LC, so liquid chromatography, where we have, for example, a separation of these molecules based on a property that they have. Like we are using a helix, so we are separating them by their polarity, so how water soluble they are. And they will separate here, so some will move faster through the column, some will move slower. And then we have the electrospray ionization, so we have to generate ions from these molecules that generally are by default not charged. So we have to create charged molecules because the mass spectrometer instrument can only detect or measure charged molecules. And that's what the MSBackend does. So it measures mass to charge ratios, and we get a two-dimensional data, so intensity against m over z, so mass to charge ratio, with these peaks that we measure here. And what one peak essentially means is, so it's the intensity is corresponding to the amount of ions with a certain mass to charge ratio that were in the sample. And here comes also the reason why we are using the LC in front of the MS, because if we would not do that, the problem with the small molecules is that we have many molecules, many compounds that are composed of exactly the same elements, so they have the same chemical formula. And with just a mass spec, we could not really know if this one signal that we have here comes from a single ion species or if it's different compounds measured at once. And that's the reason why we couple the MS with the LC, so that we have this first separation by a property that's different from mass to charge ratio, and then the separation by mass to charge ratio in the mass spec. And this LC actually adds us a third dimension that we have here, so retention time. Basically simply means that this is a time that the molecules are retained inside of the column. And typically we will measure now a sample in over like 15 minutes. And the mass spec will record a spectrum every like 250 milliseconds, so generate one spectrum. And what we get in the end is this three-dimensional data. So we have retention time, mass to charge ratio, intensity, and we can follow here what we see nicely, this ion traces. And this is, for example, where XCMS, this package, starts to identify these chromatographic peaks. And in the end of the day, what we get is what we call the LCMS features, which are characterized by having a certain mass to charge ratio and the retention time. The problem, however, is that we, at this point, have no idea what we are actually measuring. And that's also why this setup, for example, is called an untargeted metabolomics, because we don't know what these features are. We have no label on them, we have no name, no sequence. And there is, however, the possibility that we can also get a little bit of information on the structure of these ions here by fragmenting them. And a commonly used approach is the collision-induced dissociation fragmentation, where we have here a precursor ion. So this would be ions selected by the mass spec for a certain retention time, mass to charge ratio. So mass spec will collect all the ions here, and it will then accelerate them in an electrical field and throw them into a collision chamber, which is filled with a gas like nitrogen. And now we have, but what can happen here is that these precursor will hit the atoms, so the nitrogen atoms in here, and depending on the kinetic energy that's applied to this precursor, it can fall apart into smaller fragments depending on the binding energies between these different substructures. And what we get in the end is then ion fragments, and we are measuring again the mass spec, so spectrum, which is then a MS-MS or MS2 spectrum, where we have sometimes a little bit of a precursor signal, so still this unbroken, let's say, ion coming through, as well as the intensities of these individual fragments. And these MS-MS spectrum can be thought of being like a fingerprint for a molecule, for a certain setup that we have here, so certain fragmentation and instrument setup that we use. And so basically, one of the first steps in the annotation process of our features would be to compare now this fragment spectra against a reference spectrum. So we could have in-house library of such reference spectra, and when we have a match, we know more or less what compound we are actually measuring there. So that was really a very short introduction to this whole idea here. Next, I would like to give you, can I get rid of that? Introduction to the Spectra package. So that's a fairly new package that we recently added to Bioconductor. So one of the main design decisions that we made in the package is that we completely separated the user functionality from all the code that is responsible for data import, export, or representation. So we have here the Spectra object, so user will only interact with this one. And we have a second object, which is called MSBackend, or in short, just the backend, that is responsible to provide the mass spec data to the Spectra. And the advantage here is that we can now have completely different implementations of this backend to support, for example, different file formats or ways how to represent and store the data. And these can be plugged into the Spectra package and also exchanged here. And you can, as a user, simply use the same functionality that you have in the Spectra object for all your code to analyze the data. Okay, so that was now for the introduction. Let me now jump directly into RStudio. I hope I did not forget the passwords. No. So as I said, you can either watch what I'm doing here, or you could also run all these things in parallel on your own computer now or later. So whenever you log into this Docker image, what you get is this view. So we have a RStudio server version. Let me just clean up here a little bit so that I get bigger things. The font is readable, or should I increase the font size? I guess no answer means it's okay. So what we have here is the content of the package. And if you go here into the vignettes folder, we have the R Markdown file that contains all the R code for this vignette. So we could either open that one and then copy paste all the comments. What I will, however, do here is I will go into the help and just open the rendered HTML version of the vignette, just because it's looking a little bit better. So Spectra tutorials, vignettes, and here it is. Here's the vignette. So it's the same that we have seen before, just different style sheet used. And now that's what we are going to do. So the first thing we're going to do now is we want to import mass spectrometry data into R. And this is obviously fairly simple, because that's one of the main things that we need if we want to analyze mass spec data. So we load the Spectra package, and we define file names here. And these, let me make this bigger, these file names are files, so MZML files, sorry, which are bundled in the Spectra package. So raw, let's say, mass spectrometry data is usually shared as MZML files. So these keep the data that's generated by a mass spec instrument. And these four MZML files are now from a more technical experiment that we did in the lab. So we measured 8 standards, so 8 specific compounds on our LCMS setup, or actually LCMS-MS setup, to generate fragment spectra from these 8 compounds. And we, on this high IS here, for example, the standards were solved in water, and then in the second 2 files, the standards were solved in serum samples, so human serum samples. And the CE20, CE30 here means that we used 2 different collision energies to create the spectra, so the fragment spectra. Sorry. And so we have MZML files, and we can easily import now Spectra data, so MS data from MZML files with this call. So to create the Spectra, we use the Spectra constructor, we give it the file names, and here with backend, we specify one of these backend instances, so these backend classes that can handle this type of data which is provided in these files. So in this case, it's MZML files. So we use the MSBackend MZR backend, and which basically supports all raw mass spectrometry data files, so MZML, MZXML, and CDF, let's say the main ones. And what we get in the end is a Spectra object. Looks like that. So in this case, we have over 3,000 spectra here, and it tells us that we are using this type of backend. Now, what we have in this, well, let's start all the way around. So this data, what we can think of, or what the Spectra object might also be compared to a data frame, let's say, so where each row, so each element in this Spectra data frame is one spectrum, one of these 3,000 spectrum, and each column corresponds to one of the Spectra variables, so the attributes of a spectrum, like MS level, retention time, scan index. And so we have not only these 3 Spectra variables available, so there are a lot of Spectra variables that can be stored in a Spectra object. And to get them, to get a list of them, we can simply use the Spectra variables function, give it the object, and we get here all these different variables, these different attributes that we have for each spectrum in the Spectra object. And some of them are mandatory, like MS level, retention time, and data storage to data origin. Others, like the ones below here, depend also on what data is provided in the input file. So this is really stored in the MZML files, and that's why it's listed here. Okay, if we want now to access data, so extract some of these information from a Spectra object, one thing we can always do is we have accessor functions like rtime to get the retention times. I mean, I just wrap these around a head call around that to just extract the first 6 retention times here. So that's one way we can use the accessor function. But in parallel, what you can also do is we can simply treat it as it was a data frame. So we could simply say $rtime, and we would get the same information from this object. Now, as I said, this one is a MSBackend MZR. I'll use a MZR backend. And one property that I would like to explain you from this MZR backend is that it's characterized by having a, let's say, relatively low memory footprint. So you see this object here takes less than 1 megabyte of memory. And the reason for that is that the MZR backend does only hold the limited amount of data in memory. So only general spectra data is loaded into memory, but the master charge and intensity values are not present in memory, so they are retrieved on the fly from the original raw data files whenever we access, for example, MZ or intensity values. Oh, yeah, that's our beautiful error message that we get from time to time. We cannot get around that. So we have this in many different issues already. So it happens from time to time that something in R is not happy with the way how our, I guess, C++ code is called. So it should be a little bit faster. So we get here master charge ratio values for this 3000 spectra. And as you've seen, it's a little bit slower to load the data. So actually, it's quite slow, which I was surprised here. But there is also one possibility that we can do now, which was not possible in Amazon Base, for example. So we can switch backends here. So what we can do, for example, we can change now our backend from this MZR backend by calling setBackend on our Spectra object and providing the new backend that should be used. In this case, we use a MSBackend data frame. And what happened here is essentially the MSBackend data frame keeps all the data in memory, so also intensity and master charge ratio values. And for that reason, also the memory size is bigger. I mean, still it's a very small data set. So for that, it really makes sense also to load it into memory. And what we can also see is if we access now like the master charge ratio values from this object, the data access is obviously faster because we don't have to go way back to the raw data files to load that content. So I hope this was somewhat clear here. So there is always the possibility that we can switch back and forth between backends now in Spectra. And as a last thing in this section, what I would like to do is from this 3000 Spectra that we have, I would like to select some Spectra that might be fragment spectra from a molecule from metabolite called cysteine. And what I specify here is the master charge ratio, so this 241.03 would correspond to the protonated adduct, so protonated ion of this cysteine, so it's written as N plus H plus, so it's a cysteine molecule plus a hydrogen proton, and generating thereby a positively charged ion. And to select now all the spectra in this data in the Spectra object that have a precursor which matches this master charge ratio, we can simply use this function, so the filter precursor MZ, giving it our large Spectra object and specifying the master charge ratio that we would like to have. What we also do with this construction here is, so we define a lower and upper boundary for that. So this one simply calculates the master charge ratio minus 10 ppm of that, so 10 parts per million of this master charge ratio plus 10 ppm. So that's usually how we specify measurement errors in MSBack. And what we get here is now a Spectra object with 11 spectra in it. So all these matching our filtering criteria. And that's also something that we can always do. So we can subset now an object, what we can use is, we have a lot of filter functions available to subset a spectra object. And in addition, what we could also do is we could also just use the square brackets. If you would, for example, like to extract the spectra number 3 to 5, we do it in that way, so in typical R manner. Okay, with that, I would like to proceed to data processing and data manipulation with the spectra. And after that, I would like maybe to make a short break for some questions. But let me just continue with this section before. So we have seen how we can load the data, how we can represent the data. The next thing is we want to do something with the data, right? So the first thing, obviously, that we would like to do is visualizing the spectra. And for that, we can simply use plot spectra, which uses base R graphics. So no ggplot in this case. It's old school plotting that we're using here. And we want to plot the first spectrum. So we just subset our spectra object to 1. And that's what we get. So that's our fragment spectrum for this first spectrum that we have in the database. We have the mass to charge ratio values here and intensities. Quite high intensities of 120,000. And what we can also see is we have some quite nice high intensity peaks, but we have also a lot of these very low intensity signals here. And that's what I would like to get rid of now. So I would like to remove peaks here from the spectra that are below a certain intensity. And to do that, we have a function called filter intensity. And I could simply use filter intensity on our spectra object and say, well, intensity equals 1000. Then all the peaks that have an intensity below or lower than 1000 would be removed. It's simple use case, but what I would like to do is actually to remove peaks that have intensity which is lower than 5% of the highest intensity in each spectrum. So I would like to have a, let's say, dynamic filtering depending on the values in a spectrum. And the good news is we can do that because the filter intensity function also supports to get a filter function as an input parameter. And that's what we define with this construct here. So we define a simple function called low-int. And these filter functions essentially take or are expected to take as x variable the intensity values from one spectrum. And they are expected to return a logical vector with the same length. Then we have peaks in one spectrum, just with a true or false, whether or not the peak should be kept. So in our simple filter function, we simply ask for these intensities that we have, which of them are higher than the maximum intensity in the spectrum multiplied by 0.05. So which of these intensities are higher than 5% of the maximum intensity? And we can now simply call this filter intensity on our spectra object, providing this function here. And if we would now plot the data, what we see is this here. So we would really see that we got rid of a lot of these low intensity peaks, and filtering actually worked pretty well. Now, another thing I would like to do, especially for later visualization and comparison, is so here we have absolute intensities, and I would like to normalize, to scale these intensities so that the highest intensity should get a value of 100, and the others should be relative intensities to this highest intensity. Now, in the Spectra package, we don't have a dedicated normalize function implemented, but we have a very, very handy function called add processing, which allows me to perform any data manipulation to a peak matrix that I can think of. So this add processing takes as an input a function that does something on the peak matrix of each spectrum. And this peak matrix is essentially a two-column matrix. First column being the mass to charge ratio value, second column the intensities. So in our case, what we do here, we define a function called normInt, and this function takes, as I said, the peak matrix as input. Here it calculates as first the maximum intensity in this spectrum, and then it replaces the intensity column by the intensity column multiplied by 100 divided by maxint. So we are creating relative intensities to the highest intensity in the spectrum. And at last, we return this modified peak matrix again. And as I said, at processing, we can basically define any method or any function that we want here to modify the peak matrix, and we can apply it to the data simply by just saying that. And if we now intensity, if we now extract the intensities from the first spectrum, we see that we have now a filtered set. So we have intensities, and they are all relative. So they're all between 0 and 100. The funny thing that I will just briefly mention here is, however, that we did do some data manipulation. It also is listed here among these log messages, so filtering, removing peaks, and so on. However, we did in fact not change any data. And so this sounds a little bit weird, but any data manipulation that we are applying to a Spectra object, we are not applying it at that moment to the data. So the only thing that we do is we put these processings into a slot here. It's called the processing queues. So they get cached, and that's what we call then the lazy evaluation queue that we have in the Spectra object. And the big advantage of that is essentially that we can also perform data manipulations on, let's say, read-only data. Because in essence, if we would have an MZR backend, we would not like to change the mass to charge ratio and the intensity values that are in these raw data files, because it makes no sense to do that. And by using this lazy evaluation queue, we can circumvent that. So we are not changing the original data. The only thing that happens is each time that we access intensity values or mass to charge ratio values on such an object, all these data manipulations get applied on the fly to the data before it is returned to the user. So we will see also later a nice use case for that. And what this also enables us is we have this beautiful, I don't know if it's meaningful, but we have a reset function now available. And you can essentially undo data manipulations, because in essence, we are just cleaning up this processing queue. And if we would now, for example, get the intensities from this resetted spectrum for the first spectrum here, we see that we have all the intensities, so the not filtered absolute intensity values from this first spectrum. Okay, and now I would actually say we make a short break if there are any questions, maybe.
Yes, there's just a question from Thomas Naker. Is it possible to have both the raw intensities and the processed, for instance, in percentage, intensities at the same time stored in a Spectra object?
The point is you have always the raw intensities there, because we are not changing the raw intensities. But otherwise, it would. It's not really possible, I'd say. The way how you could do that is you have one Spectra object with the processing steps and one where you call reset on that, so we have them two in parallel, or you call just reset before you know what I mean? You call reset before you do any operations, and you have directly the comparison of the raw to the processed intensities or mass to charge ratio values.
Yeah.
There was also
if someone else has questions, so you can type them in the Q and answer tab, or you can also raise your hand and you can come on stage. Or if Thomas, if you want additional information, don't hesitate raising your hand.
We can also have a more extended session than later. Oh, there's another one.
Yeah. So Oliver is asking, is there support or plans for support to load vendor.raw files, or do we have to use MS-convert?
Well, it depends. I guess there are also people here in the audience that worked on that, right? Christian Panzer, for example, worked on a backend that allows to import directly the thermal files. It's always the question. In principle, you could simply implement a backend class that understands how the data can be imported, for example, from the .raw files. And that one could, again, use like the API from the vendor software to extract the intensities and mass to charge ratio values. And I mean, we don't have the support now here available and implemented, but in principle, it would be possible to do that. Sure. Okay, then I'd say we continue here. So the next thing I want to do is I want to compare spectra with each other. And to do that, we have also a function where the name already tells what it does. So it's called compare spectra. And what I'm doing here is simply calculating pairwise correlations between all the spectra that we have in this spectra object. So it's creating now a similarity matrix, 11 columns, 11 rows, and we have here comparison or similarity of the first spectrum with the first. So, well, it's compared against itself, and first against the second, first against the third, and so on. So we calculate similarities. The thing that I wanted to mention here, however, is that this compare spectra, first of all, it's a two-step approach where we have to first match the peaks between the spectra, because obviously, I mean, mass spectrometer instruments have a little bit measurement error, so we will never get exactly the same mass to charge ratio value. And that's why we, for example, have here also the parameter ppm, which allows us to match or to say that these two peaks are the same, although their mass to charge ratio value is a little bit different. So this is the first step of the compare spectra, matching the spectra, and then the similarity is calculated between the matched spectra. And maybe it's best if you have a look at the help page for this compare spectra, also to check what the defaults are. So the default similarity calculation is the normalized dot product, but we have also other functions implemented, and in near future we hope to get some more spectra similarity measures, also the ones that are used, for example, in GMPS. And also you could provide your own function again. So you could specify your own function that does some similarity calculations and provide it to this compare spectra function to do the comparison. Now, the next thing is just visualizing this correlation matrix. Be careful if you run this code on the Docker. So to me, it always happens that if I just execute that, my RStudio crashes in the Docker. I have no clue why. So the way how I get around that is that instead of plotting this, I'm saving the result directly as a PDF here. And so what we get in the end is this heat map. So we see these 11 spectra, they cluster based on their similarity into 3 clusters mainly. So we have a big one with 6 spectra in it and some others. And what we do here is simply trying to identify to which cluster each spectrum belongs. And also what we check is from which original data file are these spectra, so the spectra in each of these clusters. So and what we see here is that the biggest cluster contains all spectra that come from a file where collision energy 20 was used, and the others are for collision energy 30. And that makes obviously total sense, because if we use a different collision energy, we also generate different fragment spectra even from the same precursor ion. And what we do as a last step in this section is I want to simply or just use this spectra here that were generated with a collision energy of 20 electron volt. And oh, sorry, I have to copy this code here. And that's what we do with this call. So we simply split now our spectra object and keep the one that belongs to the first cluster. So we have now a spectra object with 6 spectra in it. Good. Now to the last part, and actually I think it's maybe the most interesting one, or the one that I'm most proud of, let's say. So it's quite nice. We can analyze the spectra data in R. So that was also possible before because we had MSM base. Now, what I think, or what we usually then do once we have the spectra, or what I would like to do here is I want to compare that against public fragment spectra, because so far we only know that these fragment spectra were generated for a precursor ion with a certain mass to charge ratio, but I can still not be sure that this is cysteine. And so in order to do that, what I would like to do is compare it against reference spectra where somebody else really verified that cysteine creates a spectrum that looks exactly like that. And fortunately enough, there are people that share their fragment spectra with the community. So there are I've just listed 4 resources where you can get fragment spectra for small molecules or small compounds. One is MassBank, we have MONA, we have Human Metabolome Database, and GMPS. So that's really nice. Also, if you have fragment spectra, please provide this your data to these resources so that also other people can take advantage of that. And so that's nice. The problem is that there is no unified way how this data can be accessed. So yes, these are all publicly available resources. Yes, you can download their data, but they all have their own format. So MassBank, for example, you can download the data as text files in their own MassBank format. MONA, you can download JSON files, one JSON file, actually a big one, where you have they have their own format. In Human Metabolome Database, you download the fragment spectra in their own XML file format, and GMPS provides the data as MGF files, so mascot generic files. Now, so it would be possible to download and then import in R and write your own code. However, what we started to do is we thought, well, maybe it's better if we just have MSBackend interface to all these resources. So we started implementing backends for Spectra for these data resources. So far, we have MassBank and HMDB implemented. And so actually, Michael Witting started implementing the MSBackend MassBank that has a backend called MSBackend MassBank, and this one allows to import and export text files in MassBank format. And I just recently also implemented a backend called MSBackend MassBank SQL, which allows me actually to directly interface and interact with the MassBank MySQL database. So that's another very good advantage or thing about MassBank, and why I like these people that generate these resources, that they now also provide their data as a MySQL database dump.
There is a question from Tobias. He is Tobias Kochman. He asks, what is the status quo of the chromatogram package? How will it interact with the Spectrum package?
Good question. We have a sticker for the chromatogram package. And we also started implementing it. I mean, the point is we wanted first to finish the Spectra package more or less so that it's settled, and then we would use the same concepts again in the chromatogram chromatogram package, so the same way with backends and so forth. But so we started with that, but I did not really have had any time to continue developing this chromatograms package in the last half a year to year. But for sure in future, I mean, once I get a little bit more time, I will work on that, because the long-term goal would actually be, I mean, I'm mostly using XCMS for untargeted metabolomics data processing, and I would like to use the Spectra object as well as the chromatograms object then for XCMS. So the chromatograms, we would have the extracted ion chromatograms for the ions to represent that, and for the spectra for all the other things. And so yes, we are going to continue developing that, and also what's let's say the glue then in the end is another package which I think it's called MS Experiment. Is that true, Laurent? I think this will be then the, let's say, the experimental wrapper for all these objects. It contains all the data from one experiment. It will have chromatograms and spectra in it. So this will then,
and we also have
we have also a sticker for that, although we did not really start the package. It's always good to start with that sticker. Okay, so I hope that answered the question. So what I'm going to do here is I'm loading the packages that I need to use. So on one hand, R MariaDB, because, okay, it's not a MySQL server, it's a MariaDB server, and also the MSBackend MassBank package. And the good thing, what I was really proud to be able to manage, is that we have in this Docker image also a MySQL server running that contains all the data from the 2020-11 release from MassBank. So I can essentially simply connect now to this MySQL database that's running inside of the container. So we have a database connection. We could also simply say DB lists, tables, it's this connection object, and it gives me information about all the database tables that are in there. So I could provide my own SQL queries to get the data. However, as I said before, we have this beautiful backend, MSBackend MassBank SQL, So what I do now is create a Spectra object which essentially represents the mass bank data. So again, I use the Spectra constructor, give it this time not file names, but our database connection. And I also have to specify which backend actually can handle this type of input object, like in this case, a database connection. So I specify MSBackend MassBank SQL. And what I get is what I want to get. Let me close this help. Search here, MBank. I have a Spectra with over 80,000 Spectra in it. So that's the content from MassBank. Again, if we look at the size of this Spectra object, it is, let's say, relatively small. And the reason for that is that if we dig into the object itself, so that's something that you should not do because you should not directly access slots from an object. So the only data that we have in this backend here is essentially the primary keys from the Spectra in the database. So we're not loading any data into memory here. Everything is in the database. And whenever we access, for example, if I want to get the MS level for the first 10 MassBank Spectra, each of these calls will cause the backend to create a SQL query, go to the database, and retrieve the data back to me. And the same way this also happens with mass-to-charge ratio value. So it's working. It's, let's say, reasonably fast. Still, I mean, what we could do here also, like before, we could load now the complete data into memory, but just changing the backend to a MSBackend data frame. But I would like just to keep it like that. So use this SQL backend so that all the data is, let's say, remote, and I'm interacting with this remote database and just getting the data that I want locally here into R. Good. Now, what does not really make sense is if I would now start to compare our 6 experimental Spectra against these 80,000 Spectra from the database, because this would take quite some time. So I will first of all just ask this question to the database. So the contains and that function will return true whenever it finds a spectrum in a Spectra object that has a peak with a certain mass-to-charge ratio value. And I use here the mass-to-charge ratio value from our precursor, so this 241 point something. So give it some measurement error or difference. We have this and that here, and it returns me true if the spectrum contains a peak with this mass-to-charge ratio value. And in the end, what we have in the MassBank database is from the over 80,000 Spectra, 217 have a peak that matches our precursor here. So what I will do next is simply subset my whole MassBank Spectra object to the one that has this peak, so only to this 217. And with this subset, comparing the Spectra is now really fast. See, we calculate now the similarity between our experimental Spectra, so the 6.1 with the 217 from the database. So that's now our similarity matrix again. And let's see, I try to also create the heat map for that. Heat. It's saving it again to a file. And we can have a look at this. Where is it? HMB. Okay, I think you can see it now. So here is basically telling us that most of these 217 Spectra do not really match our experimental Spectra, but we have a subset that have pretty high similarity. And my goal is now, let's close this one here. Let's go back to the help. I want to identify the best matching Spectra here. So I simply call which on that. And what I get is, so I have the spectrum number 4 in my Spectra object matches or has the highest similarity with the spectrum number 152 in MassBank. However, what I do next is just extracting now the intensity values for this spectrum from MassBank. So this spectrum 152. And these are the intensity values. And what we see here is we have values that are higher than 100. So this is all absolute intensity values. And I would like, for the comparison, for the plotting, I would like to have the data processed in the same way that we did with our experimental spectra. And the good thing, what I said before, is that we actually can apply the same processing. So we simply call now again our @processing function with the same normalization function on our mass bank spectra. And here is really where this lazy evaluation queue kicks in, because I mean, I'm obviously not allowed to change the intensity values or the master charge ratio values in mass bank, because these people would be very unhappy. And also, obviously, I have only a read-only connection to the database. But still, I can process the data, I can modify the data, let's say virtually. And if I get the intensities, we see that these are now again relative intensities. So all these data manipulations that I do on a Spectra object, they get applied on the fly. And the last thing we do here is we simply plot the two spectra against each other using this plot spectra mirror function, and that's the plot that's generated. So the upper panel is our experimental spectra, the lower is our mass bank spectra. The matching peaks are highlighted in blue. The numbers are just the master charge ratio of these peaks. And by looking at this one, obviously we see that our experimental spectra matches very well with the one from mass bank, and we can be fairly sure that the spectra that we generated here locally in our experiment corresponds to the same compound from which this spectrum in mass bank was created. So last thing we want to do, we want to know what is now the actual compound from which this spectrum was generated. So we can again look into what attributes we have available for the spectra from mass bank. So we have again the usual suspect, MS level, R time, and everything like that. But we have also other interesting information like the publication in which this spectrum was published. We have the splash, we have the information what adduct it is, ionization voltage, collision energy, the instruments, all these very interesting things. Problem is we have only, this one is the only reference to the compound. It's called compound ID. And that's in fact a number, and just a normal integer number. It doesn't really help us because that's the database internal ID for this compound. So it's a little bummer here, but the good news is we have implemented also an additional function in the MSBackend mass bank for this MSBackend mass bank SQL object, which is called compounds. So the thing that we do here is, first of all, we subset this mass bank to just this one best matching spectrum. And with that, we give this spectra object to this compounds function. And what this compounds function does, it's if this object uses a MSBackend mass bank SQL backend, it will go to the mass bank database and asking for the compound from which this spectrum was generated. And as a result, what you get is just a simple data frame in that case, but I cannot copy that. Copy, paste, yeah, great. Now I lost somehow my, now it's back. I have a data frame with all the compound information and annotations from the database. We have the chemical formula, we have the smiles, the INCI key, and also here the synonyms and the name. And in fact, that's cysteine, what they have in the database. So the last thing I want to do is I want to add this information as annotations, so as additional spectra variables to my spectra object. And that's also very simple. So we can also at any time add additional spectra variables to our spectra object by simply saying, like here, so our spectra object, $, the name of the new variable, and we can assign then the value to that. So what I'm doing with these 4 lines, I'm adding the name, the formula, and the adduct and collision energy to our SBS CE20. And if we look now in the spectra variables for that, what we have is we have these variables also listed here, and obviously we can also access it if we say $ like formula. We get here the information back what we recently added. Okay, now last part. So we are quite happy. We did some processing in R. We generated a spectra. We annotated it. But now we would like to export the data because it's good to have it in R, but we would also share this information with other people. So one way to share would be the MGF format, so mascot generic file format. So we would like to export this now in MGF format. And the good thing is we have a MSBackend MGF R package that Laurent implemented. And this provides a backend called MSBackend MGF. And guess what? This allows us to import and export MGF files. And that's what we're doing here. So we load now the library MSBackend MGF, and we simply call the export method on our Spectra object. We provide the Spectra object. We define a backend and also provide a file name. And the format in which a Spectra object is exported depends on the provided backend. So in this case, with MSBackend MGF, we say, please export my data as an MGF file. And to show that I'm not lying here, we simply load this MGF file back. So that's the MGF file. So it contains all the spectra. We have the spectra variables here in the type of way how MGF formats the data. And we have also the peak matrix here with the master charge and intensity values. We could also, just for fun, say something like, okay, I want to export my spectra now as MZR, as a MZML file. It's also possible, why not? Doesn't really make sense here, but I have now exported my Spectra object as a new MZML file. So in that way, we can export, we can also, let's say, flexibly define the ways and the formats in which we can export data from a Spectra object. And I think that was all. I'm actually running terribly out of time. I will skip this section here. That's just also, I mean, you can read through it. It's the way how you can compare the spectra from above against the human metabolome database, actually against the XML files that you can download from that. Just briefly go to the summary. So summarizing, I hope I could show you today a little bit that, we created a package that what we think is very flexible because it allows us to also other developers essentially to provide support for like different file types, different input formats and export formats. And and also I think another very good advantage of this is that we can also have different representations of the data. Like if you have mass spectrometry data from very large experiments, that you have backends that load only a very little amount of data into memory so that you can still process the big experiments on let's say, not too large scale computing environments. And I'd say thank you now for your time.
Thank you very much, Johannes. That was very impressive.
I would have a question for you. This last puzzle is really amazing about this MSBank interface. I was wondering, currently, how is the MSBank comparing to a, let's say, more commercial database such as NIST or something like that?
Honestly, we don't have NIST, so I cannot tell you that.
Okay.
I mean, the good thing is really that MSBank is really open source. So you're allowed to share, you're allowed to add things.
Exactly. And I think like having such an easy to use it was very convincing, and I think this will probably improve also the usage and the amount of data that will be stored, I guess. Do you think that, I don't know how it's happening, but is there a way to directly submit spectra through R? Or?
Partially. I think there is the R MSBank package that allows you to clean up fragment spectra and format them in a way that you can submit it to MSBank. But essentially what you can also do with the spectra is you can do all this analysis with spectra and use the MSBackend MSBank backend to export as text files, because that's what they want, right? They want the text files, they have it in the GitHub repository, and that's it.
Okay, super cool. Wow.
I mean,
amazing.
honestly, I started here with the MSBank people because they have a CC BY 4, I think, license. So you're really free to share the data and it's easy to access it. Also as a sort to show how you can use this, also maybe to bring more commercial vendors to open their API to their libraries, because I mean that's also what I would like to have. I would like to have a Metlin interface that I can access their Spectra library from our or also NIST libraries. This would be awesome to have.
Yeah,